Hi, good morning, my dears. I welcome you for the today's session about torque on current loop in a uniform magnetic field. What is our session? Our session is about torque on current loop in a uniform magnetic field. In the previous session, we discussed about torque definition and the nature of the uniform magnetic field. Let's see what is it. Let us consider a current loop ABCD in a uniform magnetic field. What we need to consider? Let us consider a current loop in where in a uniform magnetic field. What is that? Uniform magnetic field. So we need to give a certain name to the loop. So here I given the name of the loop is ABCD. What is that? The name of the loop is what? ABCD. So a current loop ABCD is placed in a uniform magnetic field. Where it is placed? It is placed in a uniform magnetic field. In a uniform magnetic field, we placed a current loop which is named as ABCD. So here the loop is just like a rectangular shape. The loop is considered as a rectangular shape one. So that is the reason the length of the loop is considered as L and its breadth is considered as B. So the length is what? L. Whatever loop you are considering, whatever loop you are placing in a uniform magnetic field, its length is L and breadth is B. So the length and breadth of the uniform magnetic field is L, sorry, not uniform, the current loop is L and B. So that is the reason this loop is we are considered as a rectangular one. It is considered as a rectangular shape one. Now, when place this plane loop, when a loop is placed along a applied field, so here in the same direction, that means it may you consider as parallel one. So here the plane of loop or the loop ABCD is placing if it is in applied direction or it is moving in a uniform magnetic field. So here when the loop ABCD is along the applied uniform magnetic field, so what is the condition? When the loop is what here? ABCD. When the loop ABCD is along the applied uniform magnetic field, whenever it is in same direction, if the loop is in same direction along with the applied magnetic field, you can see the structure of the rectangular loop ABCD, and it is placed between the magnetic field, that means north pole and south pole. The length of the coil is the rectangular shape is L and its breadth is B. So here this is about the schematic diagram of the our concept. So here the rectangular shape is rotating between the north and south pole in the same direction or in the perpendicular direction to the applied field. So here I took one case. Here we took the case is that the plane or the ABCD loop is in same direction. The ABCD loop is in same direction. What is happening? When the loop is in same direction along with the applied field, what was happening? The field does not, which field? The magnetic field does not exert any force on faces AD and BC. So here you have the face AD, AB, BC, CD. So here this rectangular loop or this ABCD loop is having four faces. You can see here AD, AB, BC, CD. So we have four faces, and four faces here, two faces along with the applied field, two faces along perpendicular to the applied field, means two faces along the applied magnetic field and two faces are perpendicular to the applied field. So here the first condition is that when the faces along the applied field. So what is happening? When the faces of loop ABCD, if they are in along the applied field. So here let's see what is the faces are along the applied field. So the faces along the applied field are AD and BC. So the plane loop ABCD is in along the applied uniform. When the plane loop ABCD along the applied uniform magnetic field, then what is happening? The then the field does not exert any force. In this condition, the field does not exert any force. The field, whatever field is there here, our field is that magnetic field. The magnetic field does not exert any force on faces AD and BC. So here, magnetic force will not exert any force on faces AD and BC of the loop ABCD. Why? Because they are in same direction. The loop and the applied direction. The loop of AD and BC faces and applied field of magnet both are in same direction. That is the reason the field will not show any force on faces AD and BC because of same direction, AD and BC of the loop. But in the plane loop ABCD is perpendicular to the applied field. But when the when the loop ABCD is perpendicular to the applied field, then what is happening? There in the previous condition there is no force exerted. But whenever it is in perpendicular, the field exert force on the faces AB and CD. Where? Face AB and CD. Face AB and CD. The force, whenever the plane loop ABCD is perpendicular, the field, which field? The magnetic field exert certain amount of force on face AB and CD. You can see the figure. The arrow marks are there. One is the clockwise, the another one is the anti-clockwise. So you can simply say that one. The force which is exert on faces is same in AB phase and CD phase, but they are in opposite direction. See, one is a enter into the loop, the another one is leaving out from the loop. You can see the arrow marks. The eye in the faces, the eye is entering into the loop. On the face of CD, it is leaving from the loop. So here the force is same in the face AB and CD. Whatever force is there, the force is same in the face of AB and CD, but it is in opposite direction. You can see the arrow marks there. It is in opposite direction. When it is perpendicular, the force exert on faces AB and CD. The field exert force on faces AB and CD with equal and opposite magnitude. Okay, the force is same, but the thing is that they are in opposite in magnitude. One is the entering, the another one is leaving. Therefore, the force exerted face AB is considered as what? So here force exert due to the field B on face AB is what? The force exerted on face AB it is considered as F1, which is equal to IBB, where I is current, B is the breadth, because it is it is a breadth concept, not length concept. So it is F1 is IBB, where B is the magnetic field. B is the magnetic field. So the force exerted on face AB due to field B is what? That is F1 is IBB, What is that? F1 is IBB, where I is the current, B is the breadth, and the capital B is the field. Similarly, other side of the face AB, the force exerted on face CD due to the B. What is that? The force exerted on face CD is what? F2. The first one is F1, the another one is what? F2. So here the force exerted on face CD due to B is what? That is F2, which is again IBB. You already discussed in previous slide that the force is equal, but it is in opposite in magnet. The force is same, but it is in opposite in magnitude. So both the forces of F1 and F2 of face AB and CD is same. Therefore, the forces on face AB and CD is equal and opposite in magnitude. So the net force is what? See, what is net force? Both are same magnitude. Sorry, both are in the forces are same, but their magnitude is different. So opposite magnitude. So the net force is what? One is a clockwise, the another one is anti-clockwise. One is enter, the another one is leaving. One is entering, the another one is what? The another one is leaving. You can see here from the AB phase it is entering, from the CD phase it is leaving. From the AB it is enter, from the CD it is leaving. Means the forces are equal, but they are in opposite. So the net force is what here? The net force on face AB and CD is what? It is 0. It is what? 0. It is what? 0. But here you need to consider only one thing here. The line of forces not coinciding to each other. The line of forces. So F1 and F2 both will be equal to 0. But here there is a small correction we need to understand here. What is that? The line of forces not coinciding. The line of forces are equal to 0, but the line of forces, this is about the magnetic lines characteristics, because two lines are the south pole and north pole are not coinciding. From this concept we can simply say that one, the line of forces not coinciding. Because of this reason, a torque is produced in this loop when the line of forces not coinciding. When the line of forces not coinciding, what is happening? A torque is produced. What is that? A torque is produced in the loop ABCD. What is that? In the loop ABCD, a torque is produced because line of forces not coinciding. Line of forces not coinciding. So you can see this a figure. I took a small part of the figure, that is this is about this left one is indicating about the force F1, that is AB phase, and this is indicating phase CD, and the CD phase the force Ft is activated. The force Ft is working on CD phase. Force F1 is working on AB phase. You can see here. I took from, you need to imagine the diagram, you need to analyze the diagram from AD direction, from the AD direction, from the AD to BC, BC to CD, CD to D. So here we need to analyze the diagram from AD. From where? In the view of AD. From AD we need to analyze. So from this particular segment we consider this part, that is indicating here, this one indicating F1 direction, which is equal to F1 force, which is nothing but AB phase. The another one is F2, which is indicating phase CD. So we took here phase AB and phase CD. On the phase AB, the force F1 is exerted. On phase CD, the force F2 is exerted. So F1 and F2 forces are applied on phase AB and CD. But here the line, you mentioned that one, torque, in the process of the torque concept, that is, the line of force is not coinciding. So this is the line we can imagine here. This line, it is, the line is, you are taking whatever line is there, the line it is separated into two half parts. So this is about the L by 2 and this is about the L by 2, and between this line, because of this means inflow of the current, a magnetic moment is generated. What is the magnetic moment? The magnetic moment is nothing but Ia is generated. What is Ia? Ia is nothing but magnetic moment. Because of the torque concept, because of this line not coinciding forces, line of forces not coinciding, that means that is the reason here the L we are checking into L by 2 plus L by 2. So this half is what? L by 2. The another half is that L by 2. So here L by 2 plus L by 2, that is L. So here this coinciding factor of these two characters of L by 2, L by 2 will be producing a direction of the magnetic moment to. The direction of the magnetic moment is what? That is mu equal to Ia. What is that? Mu equal to Ia, where A is the area, I is the current, mu is the magnetic moment. So here magnetic moment is generated because of the L by 2 plus L by 2, which is nothing but Ia. So here, because of this not coinciding concept of line of forces, the torque is generated with force F1 and F2 with length L by 2, which is considered as on faces AB and CD. Sorry, it is faces AB and CD. Sorry, there is a mistake. So on faces AB and CD is considered as F1 and F2. Let's see, on face AB the force is what? On face AB the force is F1, which is with a line of force, that is L by 2, IBB of L by 2. What is that? IBB of L by 2. Simply you take here, this is the CD only. On faces AB and CD is F1 and F2, where F1 is IBB of L by 2, and on CD face, that is F2, which is IBB of L by 2, where I is the current, B is the breadth, capital B is the field. Which field? Magnetic field. L by 2 is from the figure of the port of the lines coinciding concept, that is L by 2. So here now the total torque from the force F1 and F2 is what? That is, the torque is F1 plus F2, which is IBB of L by 2 plus IBB of L by 2. So after simplification, it will be IBB of L, where L by 2 plus L by 2 will be L. So here IBB of LB. But here one thing you need to understand, what is LB? The length, the product of length and breadth will be considered as what? Where LB is the area. Torque tau equal, that is not T, that is torque tau equal to F1 plus F2, which will be IB of LB. But here again I am taking one of the assumption, that is LB is where length and breadth will be equal to A. What is that? Length and breadth is A. Therefore, torque tau equal to IBA. What is that? Torque tau equal to IBA. You can use also, we can also write as tau equal to, where is IB is what? Sorry, where is IA? From the previous slide, I equal is what? Mu B. So now torque can be considered as mu B. Torque can be written as in the form of mu and B, where mu is the magnetic moment, B is the field. So you can also write this above equation as Tau can be written as what? IBA, which also can be written as tau equal to mu b. Where is mu? Mu is nothing but IA. So from this concept, this equation you can also write like as tau equal to mu b. Thank you.